everyone. Welcome to the webinar jointly organized by Global Hydrogen Economy and Powerfuels, including Hydrogen Network. My name is Ding Zhang from Particles and Catalysis Research Lab at UNSW Sydney. And I'm currently working as a postdoc in the center working on electrochemical production of ammonia and water splitting for hydrogen. And before we start, I would like to acknowledge the Bidjigal people that are the traditional custodians of the land that I'm presenting from today. I'd also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. Before we dive into the webinar, I'd like to remind everyone to mute your microphone to avoid any background noise, and also to post questions in the chat box, not the Q&A, the chat box. Please also note that this webinar will be recorded and uploaded onto Global Hydrogen Economy YouTube channel. And today I'm honored to be chairing this joint webinar, where we will be hearing from our guest speaker, Dr. Yufei Zhao, on novel electrocatalysts for highly efficient hydrogen production. For those of you who may not know Dr. Yufei Zhao, she is currently a lecturer at the University of Technology Sydney, UTS, and Dr. Zhao received her bachelor degree from Beijing Institute of Technology and dual PhD degrees from UTS and BIT. And since her graduation in 2018, she has worked as a postdoc at UTS and the University of New South Wales. And in 2020, she joined Shanghai University as an associate professor. And during her work at Shanghai University, she was also a visiting professor at the University of Toronto. And her research interest focuses on the synthesis and application of atomically dispersed catalysts, precious metal alloys, high entropy material, perovskite oxides, etc., for energy conversion reactions, including water splitting, fuel cells, and CO2 reduction reactions. Dr. Zhao has 52 publications in prestigious journals and 2 patents, and her publications have attracted more than 5,800 citations with an H-index of 35. She also serves as an editorial board member for Micromaterials and Interfaces and guest editor for the journals Energies, Materials, Discovery, Chemical Engineering. And in today's presentation, she will share her work on catalyst engineering strategies for energy conversion reactions, in particular on electrocatalysis work for acidic environments and in seawater for hydrogen production. So without further ado, over to you, Dr. Yufei Zhao.
Thank you, Dean, for your introduction. It's my great honor to be invited to present my research work in this webinar. And today, I will mainly talk about my research work related to the design and the development of this novel electrocatalyst for the highly efficient hydrogen production. As we know, due to the excessive consumption about the non-renewable energy for fossil fuels, it causes severe global problems like the energy shortage and the global warming. So the fossil fuels impacts may include the ocean acidification or extreme weather, sea level rise, plastic pollution, and so on. So now most of the researchers are trying to find renewable energy sources to replace this kind of non-renewable energy fossil fuels. There are different kinds of renewable energy sources like the solar energy, wind energy, geothermal energy, hydro energy. If we can convert this kind of renewable energy through the energy storage or conversion systems to provide electricity for our daily life, that would be great. So for my research work, we can see the research map here. I would like to utilize this kind of renewable energy and to power our water electrolyzer to produce hydrogen. For the water electrolyzer, we can see the anode side, it can oxidize this water to form the oxygen. And from the cathode side, it can reduce water to form this hydrogen. So the hydrogen we know is clean energy and has a very high mass energy density. So if we can utilize the hydrogen to replace the fossil fuels, it will create maybe a sustainable future. So for this hydrogen, after we produce the hydrogen, and we can store this hydrogen by the storage techniques, and then utilize this kind of storage by use our fuel cells. The fuel cell can work as a power to power this like transportation or our daily life usage of the electricity. By utilizing this hydrogen, we know the products is water. So the water can be reused by the water electrolyzer systems. That means for this whole system, we can see it's quite recycled very well. So it's very environmentally friendly. For my research work today, I will talk about the water electrolyzer to produce hydrogen and also talk a little bit about the fuel cells to utilize the hydrogen. For the water electrolyzer, we know it can conduct at different conditions. In the acidic condition, normally we call it a PAM water electrolyzer. For the PAM water electrolyzer, we have used the water at the anode side. The water will be oxidized to form the oxygen and the proton. The proton can transfer to the cathode side to be reduced to form the hydrogen. At the alkaline condition, we normally call it the AM water electrolyzer. For this kind of water electrolyzer, we can see it's from the cathode side, the water to be reduced, and from the anode side, the ions can be oxidized to form this to form the oxygen. So for my research with today's presentation, I will talk about the acidic condition and alkaline condition for the cathode side. That means for hydrogen evolution reactions. For the hydrogen evolution reaction, currently the benchmark catalyst is still the platinum-based electrocatalyst. It has high activity and also high stability. But we know for platinum, the problem is the high cost and also the low distribution on our Earth. So normally we try to find some strategies to modify the platinum-based electrocatalyst to reduce the cost, reduce the usage of the platinum, but still we would like to maintain the high performance and the stability. So for my research work, I'm mainly working on the platinum single atoms, platinum atomic clusters, and also platinum alloys. So we start from the single atom catalyst. For the single atom catalyst, in recent years, is a quite hot topic. When we decrease the size of the metal nanoparticles, we can see from the large size to smaller size and then to single atom catalyst. We see the exposed surface atom ratios will be increased very fast. And also for the metal atom utilization, we can see the it's also increased very fast correspondingly. When we reduce the size of the metal nanoparticles to the single atom catalyst we see here, we can assume the metal utilization can reach to almost 100%. That means all the metal deposited on the substrate can be utilized as active sites for the electrocatalytic process. Similarly, for the specific activity, we can see from the bulk to nano to sub-nano and to single atom, the specific activity also increased very fast. But the problem is the surface free energy. When we decrease the size of the nanoparticles, the surface free energy will also increase correspondingly. This increase of the surface free energy will induce in the aggregation properties of the materials. That means the single atoms, metal single atoms, all the atomic clusters may aggregate together to form nanoparticles or large particles. So in that way, we need to find a suitable support to stabilize this kind of metal single atom and also the atomic clusters and to maintain their atomically dispersed properties. The first substrate we have chosen is MXene. We know MXene is a two-dimensional materials. It's the metal carbide, metal nitride, or metal carbide nitride. So by changing the M, the metal, or the AA, we know MAX is from the max phase. Normally for the MXene, we need to etch the A element out to achieve the MXene phase. By changing the metal type and also N here, we can achieve different kind of MXene. So we have a lot of choice by using MXene as a substrate. There are also a lot of advantages of this MXene. We can see it has superior metallic conductivity, chemical stability, and also hydrophilic properties. For our experiment, we have utilized this 3-electrode system to prepare this single atom catalyst by utilizing MXene as a substrate. The system here, we use the platinum foil as a counter electrode, and during the electrocatalytic process, the platinum ions can be etched out from the platinum foil to dissolve into the electrolyte. And the dissolved platinum ions can be captured by the MXene on the working electrode to form this single atom catalyst. And also, except for forming this single atom catalyst, during this HER process, we found that the morphology has been changed. Here, the SEM image and also the schematic illustration showing that during the electrochemical process, the loosely packed MXene, this MXene achieved by etching the A element from the max to achieve this MXene, has been exfoliated to the two-dimensional nanosheets. So That means during this electrochemical process, the electrochemical exfoliation and the deposition of single PT atoms occurred at the same time. We have used the high resolution TM to confirm the exfoliated properties of this MXene. And then we use a hard disk stem image to see the bright dots here on the substrate. Due to the different atomic number between the molybdenum and the substrate, we ascribe this kind of bright dots to the platinum atoms. When zooming in, we found that this kind of bright dots sit at the position of the molybdenum. In order to investigate how they positions between the platinum and the substrate, we have conducted a comparison experiment by exchanging the counter electrode here from the platinum foil to the graphite rod. When we utilize the graphite rod as a counter electrode, that means there's no platinum in this system. We found a lot of vacancies has been formed on the surface of this MXene. So by comparing these two images, we assume that this platinum has occupied these vacancies to form the single atom catalyst. And we have also done the hard disk stem image simulation by removing the molybdenum atoms and put the platinum atoms in. We see these two images are quite similar. So it should be the platinum occupied vacancy and stabilized by the substrate. For the XAS result here, we can see the our catalysts show one dominant peak here between 1 to 2. That means the platinum single atom has been stabilized by the light atom, and also the Xene results show the valence state of this platinum is between the platinum foil and the platinum O2. That means the valence state should be between 0 to 4. This is LSV result we have achieved during this electrochemical process. From the initial cycle to the 1000 cycle, we can see the performance increased from initial to 100 to 300 to 1000 cycles. That means during this process, the MXene has been exfoliated and also the platinum single atom has been deposited on the MXene. And in order to investigate how the exfoliated can be occurred during this electrochemical process, we assume that the protons may play quite an important role during this process. And we have conducted the experiments by using the graphite rod as a counter electrode and conducted this experiment at different pH solutions. We can see in acidic conditions, the performance increased, but the trend has been decreased when we increase the pH from 0 to 2. That means the high concentration protons are beneficial for this process. In the neutral conditions, we can see performance maintain almost no change. In the alkaline conditions, the performance decreased a little bit, but decreased performance may attribute it to the deactivation of the MXene in alkaline conditions, or the interactions between the positively charged potassium with the negatively charged oxygen termination here. But from this experiment, we can see the change of the pH, the performance decreased according. The increased trend decreased, and from this way, from neutral to alkaline, the performance decreased a little bit. That means the protons in the electrolyte indeed play quite an important role for the exfoliation of the MXene. Based on the experimental result, we have proposed the mechanism for the MXene exfoliation and also for the single atom immobilization. During the HER process, the proton will be interacted with the oxygen termination here, because for the previous publication or the DFT calculation, they have confirmed that the oxygen termination normally the active sites from the MXene for the HER process. So it should be interact with the oxygen first and to produce hydrogen. And the continuous generation of the hydrogen during this HER process will make the MXene to be exfoliated from the loosely packed structure to form this exfoliated two-dimensional nanoshades. And also the interaction between the hydrogen and oxygen may form the OH2 structure. This structure may drag the molybdenum out from the structure to form the molybdenum vacancy, and the platinum ions can be captured by the vacancy to form this kind of single atom catalyst. And when we utilize this single atom catalyst for HER, we can see the mass activity is really high. is about 40 times higher than the commercial platinum carbon. That means we can highly reduce the usage of the platinum, but still we can keep very high catalytic activity for the HER process. For the platinum single atom catalyst, we know the platinum atoms are randomly distributed on the substrate. So the interactions between the platinum atoms can be negligible. So recently, another topic is based on the atomic clusters. That means with a few metal atoms together, but still they keep atomically dispersed properties. In this kind of atomic structure, we can see it possesses the advantages of quite a small contact angle with the support. That means it's different from the nanoparticles with very obvious 3D structures. For this kind of atomic clusters, normally it has quite flat structure to maintain the strong interaction between the atomic cluster and the support. And also it possesses the nearby atoms. That means the potential synergistic interactions between the metal atoms may further boost the HER process. So keeping this in mind, we have designed this kind of atomic clusters. For atomic cluster, as I talked, the surface free energy is also very high. It's similar to the single atom catalyst. So we need to find a very strong support to stabilize this atomic cluster. Here, the substrate we have found is the cobalt single atoms. We have used these cobalt single atoms to stabilize this atomic cluster and form this protrusive structure. For this kind of structure, it's to make it easier to interact with the reactant and facilitate the HER process. After the obtain this material, we have to do the characterization. We can see there's no particles here. That means all the platinum has maintained as the atomic cluster. The diameters is lower than 1 nanometers. And also when we zoom in, we can find the different contrast of the bright dots. The higher contrast we ascribe it to platinum, and the lower contrast we ascribe it to the cobalt. When we see one atomic cluster here, we can find also different contrast of the atoms shown here. So we also done the the simulation to see if we put these bright dots to the platinum and these lower bright dots to the cobalt, it shows quite a similar morphology to the experimental result. So that means it may form the close interaction between the platinum and the cobalt. The strong interaction may modify the electron structure of the platinum and the cobalt. And here is a line scan. If we give the line scan to the similar bright dots, we can see it can form the single atomic layer of platinum. If we did the line scan for the different contrast of the dots, we can see the close interaction of the cobalt and the platinum. And then we have done the EDS line scan for the one single atomic clusters. We can see the similar trend of the platinum and oxygen. That means for this atomic cluster, it may not the metallic atomic cluster, but the oxygen here to link these platinum atoms together to form this a little bit oxidized cluster for the HER. And then for the electronic structure, we have done like the XPS. For the XPS, we can see except for synthesizing this atomic cluster, we have also prepared single atom and nanoparticles as comparison. So for this kind of different samples, we can see compare with the pure cobalt single atom catalyst. The single atom and atomic clusters show the peak shift. That means after incorporating the single atom and atomic cluster of PT, it formed the interaction with the substrate cobalt atoms. So the interactions between cobalt and platinum occurred to leave the peak shift. Also, we have calculated the platinum, the valence state of the platinum. After the calculation based on the Xing result, we can see the valence state of the atomic cluster PT is lower than the single atom PT. That means the lower valence state of the PT may possess the higher electron density to facilitate the HER and may achieve the better performance compared to the single atom. And for the exact result for cobalt, we can see there is almost no change after we incorporating the PT species. It's still keep the original coordination environment. So that means the incorporation of PT doesn't achieve change the environment of the cobalt. For the platinum, we have done the simulation to achieve the atomic structure. And the performance we can see here, it shows quite high performance for the HER in acidic condition, and it's slightly better for the compared to the commercial platinum. But for the mass activity, it's much higher than the platinum because it's a much higher loading of platinum on the. For the commercial platinum, it's much higher loading of platinum on carbon, but for ours, the loading is quite low. So for mass activity, it shows very good performance. When compared with the other published PT-based catalysts, still our catalysts show much higher mass activity and also the low Taffel slope. And then we have constructed the atomic structure, try to explain why this material has shown really good performance and where is the active size of this material. As it is shown here, we have constructed this platinum-oxygen-platinum atomic clusters, which is stabilized by the cobalt single atoms here. And from this atomic structure, we can find the two units may be the active size for the HER. One is from the interface, is cobalt, oxygen, platinum here. And another one should be the platinum, oxygen, platinum on top of these clusters. When we do the charge redistribution, we found that in the interface, there are very heavy charge has been transferred from the metal to oxygen. But from the on top of the platinum, oxygen, platinum part, there are much less electron has been transferred. That means for the platinum here, in the unit of the platinum, oxygen, platinum, there's much high electron density compared to the interface. So this site may be the contribute more to the HER catalytic activity. And also when we calculate the free energy of this atomic cluster and the single atom for the HER, we found the atomic cluster show much better performance compared to the single atoms. So that means the platinum, oxygen, platinum unit is very good place or active size for the HER. Except for working on the single atom and working on the atomic clusters, we have also done a few works on the alloys. For the PT-based alloys, we normally incorporate the non-precious metals like the transition metals into these PT structures and to lower the cost and also modify the electronic structure of the platinum. Like this picture, we try to use different method and then to expose more PT on the surface. Because for the electrocatalytic, we know the reactants need to be interact with the active size and to accelerate this process. So if we expose more platinum on the surface of these materials, that means that all the exposed platinum can act as the active size for the HER process. So we have utilized this AAO template to with the electrochemical deposition method to deposit the platinum, cobalt, ruthenium to form this kind of the nanowire structure. Here, the ruthenium here is a very low count. We incorporate the ruthenium is to facilitate the water dissolution because this material we have used it for alkaline HER. And by synthesize its platinum cobalt alloys and with the low amount of ruthenium, we have achieved very good performance. And by the high resolution TM, we can see the obvious lattice is ascribed to the platinum. So we assume that the surface may platinum-rich surface with the alloys inside. We have utilized this material for the alkaline HER. We can see the performance is really good. For the overpotential of 8, we can achieve the current density of 10 milliampere per centimeter square. For the overpotential of 112, can achieve the current density of 100 milliampere per centimeter square, which is much better than the other compositions like the platinum cobalt, platinum ruthenium, or the cobalt ruthenium, and so on. When we compare with the other catalyst, we can see our materials also show quite good performance. And here is we try to use the method to confirm that the surface is platinum rich. We have used acid to treat these materials to remove, if the surface is platinum cobalt alloys, we can use acid to remove the cobalt on the surface. But when we use acid to treat these materials, we find the performance almost no change and become a little bit better. So that means there is most of the cobalt has been inside of these nanowires, and the surface is platinum enriched. Also, we have changed the content of the ruthenium to investigate the role of ruthenium on the performance of the alkaline HER. For the ruthenium one here, we found if we lower the ruthenium or enhance the ruthenium content, the performance changes a little bit, but not that much. So the ruthenium may also contribute a lot to this alkaline HER process. And then we have conducted the DFT. The atomic structure we have set up here is with the platinum cobalt alloys as inside, and the platinum surface, we can see platinum-rich surface. And we have changed some atoms from the platinum to the ruthenium. We have calculated the hydrogen absorption energy on the ruthenium and on platinum. We found the platinum has better absorption energy compared to the ruthenium. So this site, the platinum-rich surface, the platinum site should be the active site for the hydrogen absorption. But for the water absorption and the desorption, we found the ruthenium has optimized the energy compared to the platinum. So for this material, the mechanism should be the water first absorbed on the ruthenium side, and the water dissolution have occurred also on the ruthenium side, and then the generated protons can be transferred to the platinum side and to produce hydrogen. And currently, we are working on the partially oxidized platinum alloys. That means the valence state of the platinum may also contribute to the performance of this HER. There is previously one publication. They have investigated the reduced of the ruthenium oxide. It show better performance for HER compared to the pure ruthenium and the ruthenium oxide. They have demonstrated that they form this reduced ruthenium oxide may make it easier to form this kind of interface, ruthenium oxide, and this interface can facilitate the HER. So for our case, we have prepared this platinum alloys first, it's platinum ruthenium, and then we try to reduce and oxidize this platinum ruthenium to achieve the reduced and oxidized samples to investigate the influence from the valence state for the HER performance. We have done the characterization. Here is XPS and XAS. For the XPS, we can see for platinum and the ruthenium, the valence state of these two elements should be sit between the platinum ruthenium reduced and oxidized samples. And for the XAS here, we can see the Xine result. The platinum should sit between the valence state of 0 to 4+. And for the ruthenium, also it sits between the ruthenium foil and also ruthenium dioxide. When we utilize this material for HER, we found that this platinum ruthenium show much better performance than the reduced and oxidized platinum ruthenium. So that means the valence state of this platinum ruthenium in the alloys may play quite an important role for the alkaline condition HER. And currently, we are utilizing the in situ characterizations to further investigate why this change of the valence state can highly affect the performance for the HER. Now we go back to this research map. For the water splitting, we know it can generate hydrogen, and hydrogen can be used as the fuels for the fuel cells. So for the fuel cells, I will talk about a little bit research work for this kind of fuel cells, how to utilize the hydrogen to provide energy. So for fuel cells, we know for the cathode side is oxygen reduction. For the anode side is hydrogen oxidation. For my research work, I'm mainly working on these oxygen reduction reactions in the fuel cells. For the oxygen reduction reaction, we know normally the catalyst is still the noble metal catalyst or the non-noble metal catalyst. For the noble catalyst, it's similar to HER, so it's rely on the platinum-based catalyst. For the non-noble catalyst, we know iron is a very promising catalyst to replace the platinum-based catalyst. For the iron, especially for iron single atom catalyst, we know the typical atomic structure should be the iron nitrogen 4. It's a very popular single atom catalyst that has been investigated. If we want to further enhance the performance of this iron nitrogen 4 atomic structures, we can do the first coordination sphere engineering or the second coordination sphere and beyond do the engineering to change the electronic structure of the center metals. The first coordination shell sphere engineering, such as we can change the number of nitrogen here to form the nitrogen 2, nitrogen 3, 5, 6, or even we can form these dimer structures. And also we can incorporate the other heteroatoms like the phosphorus, the sulfur to engineer this iron-based single atom catalyst. So for my research work, the first one, we would like to tune in the coordination environment of the iron-based catalyst. The method we have used is by utilizing the same carbon precursor by changing of these different metal ions like the iron, cobalt, nickel. We found it can achieve quite different atomic structures. We assume that the interactions or the affinity between these ions and the ligands in the carbon precursors induced to the different atomic structures. For the iron, we can see it formed the atomic structure with the iron directly bonded with 4 nitrogen, and the sulfur atoms are in the second coordination shells. For the cobalt and the nickel, it's different. For the cobalt and the nickel, we can see it bond with 3 nitrogen with 1 sulfur here. So the different atomic structures between the iron, cobalt, and nickel may lead to the different charge or electron transfer in kind of these atomic structures. And that way will make the center metals have different charge density, so show different performance for this ORR. When we use this material for ORR, we can see the iron one with the atomic structure of the iron, nitrogen 4, sulfur 2 show the best performance compared to the cobalt and nickel one. And for it's a 4 electron process to produce water as the products. Also, it shows very high methanol tolerance and stability here. We try to use the DFT to explain why this kind of atomic structure can show quite good performance for ORR. First, we have calculated the charge density. For this atomic structure, with the sulfur in the second coordination shell, it shows higher charge density compared to this atomic structure with the sulfur in the first coordination shell. And also for this atomic structure, it can facilitate the ORR by optimizing the free energy here. We can see it can highly improve the ORR process. And based on this atomic structure, we further try to incorporate other functional groups to improve the performance. We have used the DFT to calculate, to incorporate these epoxy groups. We have constructed 3 different structures by incorporating these epoxy groups to this iron, nitrogen 4, sulfur 2 structure. When we put the epoxy group here and here, this is called structure 1, structure 2. For the third structure, we have put the epoxy groups on top of this carbon and the sulfur atoms. But after the optimization, we found the first 2 structures are quite stable, and the third structures are not stable. This bond between the oxygen and the sulfur will be break. So for the first structures, we have calculated the ORR performance for the free energy. We found that the structure 1 showed the best performance. We have also compared the performance of the structure 1 to iron, nitrogen 4 and the iron, nitrogen 4, sulfur 2. And also the structure 1, we can see show the best performance based on the DFT calculation. So we found that further incorporating of this epoxy group can further enhance the electrochemical performance of the ORR of this active center. And also the position of this epoxy group also is important for the ORR performance. Here is the material we have prepared. We have used the CMK3 as a substrate to support these iron single atoms. And we found the material we have achieved by using the XPS. It showed the dominant peaks of these epoxy groups. And here is the AS result to do the simulation. It shows the atomic structure. And also the performance of this material is really good. It showed the halfway potential more than 0.9, is around 0.92. And then we try to investigate whether the epoxy group indeed affect the catalytic performance for ORR. We try to use a chemical treat this material to destroy this epoxy group and to see whether the performance will be changed. And after the treatment by the oxidation and the reduction, we found for sulfur is almost no change here. But for the oxygen, the epoxy group, the domination trend has been decreased. The epoxy group has been changed to the other oxygen groups here. And accordingly, we can see the performance decrease very obvious after the oxidation and the reduction. So that means this epoxy group indeed play quite important role to further boost the OR catalytic activity of this iron, nitrogen 4, and sulfur 2. So we have proposed the mechanism, except for modulating the electronic structure of the iron in this atomic structure. This epoxy group may also participate into the reactions. It can form this reversible cleavage of this epoxy to form the oxygen and carbon with negative charged or the positively charged, and facilitate this rate determining steps, and then to facilitate the OR process. That's the research work I'm talking about is for hydrogen evolution and for oxygen evolution, oxygen reduction reaction. As Dean introduced in my research group, we are also working on the oxygen evolution reaction. For the oxygen evolution reaction currently, especially for the acidic oxygen evolution reaction and the seawater oxygen evolution reaction, currently we are all working on this part. So hopefully we can generate some good results by these two research directions. And also we have done some work for the CO2 reduction reactions. So no matter for which kind of energy conversion reactions, we can see for HER, for OR, for OER, or for CO2R, they all require the design and the development of this highly efficient catalyst. So the material is very important. And also for the material design strategies for this atomically dispersed electrocatalyst, we can see the coordination environment engineering strategies is quite important to modify the electron structure of the center metals, and then for the high performance of the energy conversion reactions. And the third one is the correlations between the structures and activity. Currently, is also very important. We now use the in situ characterizations to monitor the dynamic change during this electrocatalytic process. So except for only characterized our materials, we can know more details about how the material will change under this kind of electrocatalytic process, and then to understand more about the materials and the dynamic process. So that's all for my today's presentation. Thank you for your attention.
For sharing your wonderful work with us. So if anyone has any questions, just feel free to put in the chat box. And I think I have two questions, Yufei. So my first question is, we can incorporate platinum on different substrate like MXene, carbon, and metal oxide. And which type of substrate do you think is promising in terms of like scalability and stability, like for the future scale up hydrogen production?
I think that depends on like the different conditions. For MXene, let me go back to MXene. For the MXene, it's quite stable, especially in acidic conditions. We know acidic is quite corrosive, but for the MXene, from how to make the MXene, we need to etch the element out from the max phase. So for the MXene, it's extremely stable in acidic conditions. But for the how to scale up of the MXene, I think maybe compared to the carbon material, it has not that promising compared to the carbon material. But for the stability, I think MXene may be better than the carbon material. And for the metal alloys, currently we are working on the usage of the platinum compared to use a substrate of the carbon material or MXene. Definitely to use higher deposition of this platinum on this substrate. But the high deposition, it will increase the cost, but maybe it can further enhance the performance with more active size. So I think each of them may have some advantages. So we can utilize their advantages, and maybe if we can combine some advantages together, maybe we can make better catalyst for the HER.
Okay, thank you very much. I think Rose has a question. So for platinum single atom on MaxSync, you reported the mass activity is 40 times higher than that of platinum carbon. But how about the activity per centimeter square of the electrode, or the overall yield of the hydrogen, the productivity of hydrogen?
The electrochemical performance mass activity is high. It is because the loading of the platinum on the MaxSync is quite low. So compared to the commercial platinum carbon, it's a really high mass activity. For the LSV readout, I cannot remember. The overpotential should be around 30 millivolt to achieve the current density of 10 milliampere per centimeter square. So it's also very high, very good. And for MaxSync, I think if we want to develop some electrocatalyst for in acidic condition by utilizing MaxSync, actually we have a lot of choice, especially for the molybdenum or tungsten-based MaxSync. We can choose to utilize it as the substrate to support our single atom or atomic clusters because it's quite stable in acidic conditions.
Okay, and then we get another question. So you have done a lot of work on single atoms, atomic clusters, and nanometals. And which one do you think is the best candidate for the potential future industrial applications for hydrogen production?
If we working on the HER side, and if we want to reduce the usage of for the industry, we definitely want to reduce the cost and reduce the usage of the platinum. So if in that way, I think the single atom and the atomic clusters should be better. The usage of the single atom or atomic clusters normally for the PT deposited on the substrate is around 1%, or even we can make it lower, like the atomic cluster for this one, we make it to 0.5, still it can show very high performance. But for the here is for the HER side, but for OER side, I haven't talked about the OER here, but for OER side, we have tried a single atom, but for the OER, it's a 4-electron process. So for OER side, still now we are working on the oxide, ruthenium oxide materials, not for the single atom. For single atom, is randomly distributed. It's hard for this 4-electron systems. For the HER, it's 2-electron transfer, so it's much better by utilizing this kind of atomic clusters or the single atoms.
Okay. And any more questions from the audience? Yeah, actually, I'm also interested in acidic OER because I feel like in acidic OER, metal oxide has been extensively studied. So I'm also wondering, like, if we can incorporate some precious metals on metal oxide for HER, and then we can sort of produce like bifunctional material for HER and OER, so we can reduce the cost of material synthesis. And what's your opinion on this?
Yeah, currently, actually, we try to working on because if you want to work on both, I mean HER and OER. Normally for HER, we would like or we prefer the lower valence state of the metals, but for OER, normally we would like to higher valence state of the metals. So if we design the materials, maybe we have different strategies. But if we want to design the bifunctional materials, and we would like to reduce usage of the precious metals, we can find some suitable like the metal compound as a substrate and by incorporating in the precious metals. But for the precious metals, it's also a little bit different because if we want to work on the acidic conditions, normally for HER side, we would like to use the platinum. If we want to work on the alkaline conditions, maybe ruthenium is a better choice. But for OER, currently we don't want to use the uridium because it's too expensive. Yeah. So we use the ruthenium as an alternative. So if for alkaline conditions, I think ruthenium can work on both. I mean for HER and for OER. But for the acidic conditions, we can combine platinum with ruthenium. But if we only use the platinum or use ruthenium, maybe not that good.
Yeah, exactly. Yeah. Okay, I have one more question. Is there any structural reconstruction of your single atom catalyst in both acidic and alkaline electrolyte? Will the stability be affected because of this issue?
For the MaxSync-based one, it's not good in the alkaline conditions. So even though we only test the MaxSync, there's no single atom, only the MaxSync we can see in the alkaline condition is not that stable. Especially when we increase the concentrations of the alkaline condition, it will react with the alkaline. So for the MXene, I think it's a good catalyst in acidic conditions, but not in the alkaline conditions. For the atomic cluster, actually for this one, we have worked on the platinum atomic clusters and also ruthenium and the iridium atomic clusters. So I think for this one, for our material, we have tested it in both acidic and alkaline conditions. And for the platinum, it shows slightly better performance in acidic compared to the alkaline conditions. But for the ruthenium one, the atomic cluster, it shows quite good performance in alkaline conditions. So for the carbon support, we know it's stable at both in HER condition. I mean, it is stable for both acidic and alkaline conditions. But when we design the OER catalyst, we normally don't want to use any carbon-based materials. So for the carbon straight, it's not suitable for OER side. But for HER, normally still we utilize the carbon as a support. It's cheap and also it's easy to make large amounts.
Okay. Any more questions from the audience? I'll just give maybe just 1 more minute to put more questions. Nope. All right. Okay. I think that's the end of this webinar. And if you have any more questions, just please feel free to reach out to our speaker, Dr. Yufei Zhao, through LinkedIn or to contact us. And finally, I'd also like to appreciate your wonderful work, Dr. Yufei Zhao, for sharing your invaluable insights and expertise with us. And also don't forget to check out Global Hydrogen YouTube channel for our previous webinars. And thank you very much again for joining us and have a wonderful day.
Thank you. Thank you so much.